Have you ever tried to predict the future, like really predict it, but felt like the world is just too messy, too uncertain? Maybe you're trying to build an AI that can recognize a face in a blurry photo, or decide if a medical scan shows a tumor, or even forecast the weather. But here's the catch: real life isn't clean. Data is noisy. Images are fuzzy. Sensors fail. And sometimes there's more than one right answer. So how do we teach machines to deal with uncertainty? Today, we're diving into one of the coolest ideas in modern AI: learning in an uncertain world by representing ambiguity through multiple hypotheses. Imagine your AI doesn't just say, "I think it's a cat," but instead says, "I'm not 100% sure, but here are a few possibilities ranked by confidence." That's the power of probabilistic modeling, and more specifically, something called normalizing flows. Now you might be thinking, wait, what's a normalizing flow? Think of it like a shape-shifting pipeline for data. Imagine you have a bunch of random points scattered across a space, like stars in the night sky. You want to understand the pattern behind them. But instead of just guessing, you want to transform those points into a clean, familiar shape, like a perfect bell curve, so you can analyze it easily. That's exactly what normalizing flows do. They take complicated, messy data distributions, like the wild spread of real-world sensor readings, and smoothly morph them into simple, known distributions. But here's the genius part: this transformation isn't just one way. The model learns both how to go from simple to complex, and back again. So when you give it a new input, like a new image or weather reading, it doesn't just spit out a single guess. It says, "Based on everything I've learned, here are several possible outcomes, and how likely each one is." This is uncertainty quantification, and it's a game changer. Why does this matter? Well, imagine self-driving cars. If the system sees a shadow in the road, it shouldn't just say it's a pothole. It should say, "There's a 60% chance it's a pothole, 30% it's a plastic bag, and 10% it's a small animal." That kind of honest uncertainty is what keeps us safe. And this idea didn't come out of nowhere. It builds on decades of math from mixture models. Think, combining multiple bell curves to represent complex data, to information theory, the science of measuring uncertainty, to variational inference, a fancy way of approximating complex probabilities. But the real breakthrough came in the 2010s with papers like NICE and Real NVP, which introduced normalizing flows as a practical, scalable tool. These models use a series of simple, invertible transformations, like stacking mirrors that bend light in just the right way, to build up incredibly complex probability distributions. And because they're invertible, we can calculate exact probabilities, not just estimates. It's like having a machine that can not only predict the future, but also explain why it's not 100% sure. This isn't just theory. Normalizing flows are being used in medicine, climate modeling, robotics, even in analyzing ancient texts. They help us understand the limits of our knowledge, which is just as important as knowing what we do know. And the best part? They're becoming easier to use. Libraries like TensorFlow and PyTorch now have built-in tools to build and train them. So next time you see an AI making a decision, pause and ask, is it just guessing, or is it thinking in probabilities? Because the most intelligent systems aren't the ones that are always right. They're the ones that know when they're unsure. Thanks for watching. If you found this mind-blowing, hit like, subscribe, and drop a comment. What kind of uncertainty would you want AI to handle better? Until next time, stay curious, stay uncertain, and keep learning. Imagine you're a self-driving car. A pedestrian steps into the road. Your AI doesn't just say they're probably there. It says, "There's a 60% chance they'll stop, a 30% chance they'll dart left, and a 10% chance they'll run right, and here's why." That's not science fiction. It's the future of AI, powered by something straight out of quantum physics. Today, we're diving into a revolutionary new AI model called the Schrödinger Neural Network, or SNN. It's not just another machine learning tool. It's a paradigm shift, where predictions aren't just numbers but waves of possibility. Most AI models today work like a single-point guesser. Give it a picture, it says cat. Give it a weather report, it says 25 degrees, but real life. It's messy, uncertain, full of multiple possible outcomes. Traditional models struggle with this. They either collapse complex reality into one number, or they get overwhelmed trying to list every possibility. Enter the Schrödinger Neural Network. Instead of predicting a single value, the SNN predicts a wave, a complex oscillating function called a wavefunction. Think of it like a musical note played on a piano string. It's not just one pitch, but a whole harmony of vibrations. And here's the magic: the probability of any outcome. It's not guessed. It's calculated by squaring the height of the wave at that point. That's not a metaphor, it's Born's rule, a cornerstone of quantum mechanics. So if the wave is high in one spot, that outcome is likely. If it's low in another, it's unlikely. And if the wave has multiple peaks, that's not a bug, it's a feature. It means the model naturally sees multiple possible futures. No mixtures, no complex math. Just waves interfering with each other, constructively forming peaks, destructively canceling valleys, creating multimodal predictions without even trying. This is why SNNs are so powerful. They don't assume there are multiple modes. They discover them through interference, just like light waves create rainbows. And because the wave is built from Chebyshev polynomials, A mathematically stable family of functions. The model stays accurate, avoids numerical errors, and keeps the total probability perfectly normalized. No more probability overflow or missing mass. Even better, the phase of the wave, its timing, its rhythm matters. It's invisible in the final probability, but it controls how the wave interferes. Complex coefficients let the model fine-tune this phase, shaping peaks and valleys with surgical precision, without adding more parameters. It's like having a secret lever to sculpt uncertainty. Now here's where it gets really smart. The SNN isn't just flexible, it's physically informed. It uses kinetic energy and potential energy, concepts from quantum physics, as regularization. Think of it like this: if a wave is too jagged or too sharp, it's expensive in energy. So the model learns to balance sharpness for accuracy with smoothness for stability. It's like tuning a guitar: too tight it snaps. Too loose it sounds dull. The SNN finds the sweet spot. This isn't just theory. It's practical. You can control how much the model wants to focus on one outcome versus spreading uncertainty. Want a conservative, safe prediction? Crank up the smoothness. Want it to be precise, even if risky? Let it sharpen. And when it comes to real-world problems, like predicting the hidden state behind noisy data, the SNN wins. In one test, the model had to reverse engineer a hidden variable from a nonlinear, many-to-one relationship. Traditional models, they'd smear probability across valleys, inventing false certainty. But the SNN, it respects the geometry. It places mass exactly where the physics says it should, on the ridges, not the valleys. This isn't just about better predictions. It's about trustworthy uncertainty. Because the model doesn't just predict, it explains. You can ask, how confident is it? Where are the weak spots? Is it overfitting? And the answers come from simple analytical calculations, quadratic forms in coefficient space. No sampling. No approximations. The Schrödinger Neural Network isn't just a new tool. It's a new way of thinking. Where traditional AI sees a single answer, the SNN sees a spectrum of possibilities. Where others struggle with uncertainty, the SNN embraces it, using the laws of physics to guide its intelligence. It's not about replacing old models. It's about elevating prediction, from a point estimate to a coherent, physically grounded, and deeply uncertain view of the world. And in a world full of surprises, that's not just smart. It's essential. Because sometimes the most powerful thing an AI can do is admit it doesn't know everything.